Well, welcome, Susan. It's really fabulous to have you here with us at Microsoft Research. Of course, Microsoft is almost a home for you in some ways.
That's right. It's
You
great
were-
to be here.
Yeah, and you were our chief economist. What years was that?
Well, so I started in 2007, and I think they endowed me with that fancy title in early
great title.
2008, and really there hadn't been a chief economist, and so they decided to create one. And I sort of describe it as consulting chief economist because I had a mix of sort of full-time as a VR for a while, and then part-time. And I did that for about 7 years.
And just so folks out there know what a VR is, visiting researchership.
Exactly. So Microsoft Research has this great program where without resigning your university position, you can basically be full-time at Microsoft. And so I had a home in Microsoft Research, but was also spending a lot of time with the business as well.
Now, jumping way back in time, not that far back, to your early college years, I'm just curious, because a lot of our folks that come and watch these fireside chats are very interested in careers and mentorship and folks who inspired folks to do what they now do in the world. And I'm curious about your own education and experience. You were at Duke, and it seems you were so excited about so many things. You had multiple majors. So what went on in your early days of college in terms of your thinking about career and topics of interest?
Sure. So I actually started in computer science, and I had gotten a little bit of exposure to computer science in as a summer job selling computers to the government the summer before college. And so I decided I wanted to do computer science, and I just took a few economics classes because I thought maybe I would go to a startup. Of course, going to a startup in the late 80s wasn't really the trendy thing to do, but it seemed intriguing to me. Then I learned about economics, and I actually had a professor in economics who picked me out to be his research assistant. And I actually started administering his workstation. And he said, "Oh, I'd love it if you got a PhD in economics." And I said, "Well, I don't really think I'm
This
going
as
to."
an undergraduate.
As an undergraduate, yeah.
Administering his workstation, and he happened to just mention this
Well,
in passing.
he was really looking to mentor students to go on to get PhDs, and he'd had a number of wonderful undergraduates. And actually, it's a nice thing about being at a program that has a good PhD program but not a great PhD program, because at Duke the undergraduates were a little stronger on average than the PhD students, and so he had been recruiting undergraduate research
That's
assistants.
interesting. What was his name?
Bob Marshall.
And so did you view him as an inspiring force in your life at that point? Or
Well,
branching into-
at first, I just liked administering a Unix workstation better than washing test tubes, which was my next best work study alternative to pay for my school. But then over time, I actually got very excited about economics. And at the time, computer science was maybe a little bit more theoretical and abstract. And so I loved it, but it was a little bit harder to see the mapping beyond programming, the mapping from really the research side of computer science to things that were more practical. I know it sounds crazy now because, of course, computer science is applied everywhere. But in economics, I felt a little bit more of a natural way to see how the research would change the world. And so I liked the impact of economics. And I actually worked on a bunch of policy problems with this professor. And he really showed me how he ended up testifying before Congress on something I worked with him on. And so I got excited about that. But I never lost my love of computer science. So I finished the computer science major and the economics major. The math major came along the way because I had taken a pretty theoretical computer science approach. And I also needed a good math to get into the best PhD programs. But then I went into the economic direction and studied auctions, but I never sort of lost that love of computer science. And so it was then, as I got further in my career, that these things kind of came back together in really interesting ways.
Yeah. So shifting to topical, it seems there's a thread of fascination that you've had with action or decisions under uncertainty and sort of grappling with uncertainty in the world, and looking at economics through that lens of action decision making. You have any comments about this idea of this passion or interest in uncertainty and probability?
I would say that generally my interest in theoretical issues has always been as a means to an end. So early in my career, I was interested in studying problems about auctions and mechanism design, and then there were some technical issues that needed to be solved to really make that theory beautiful. And so in some ways it was a little bit unnatural for me because I got more theoretical and I became very well known for very theoretical work. And I loved doing it. It was beautiful, but actually it wasn't my main motivation. My main motivation was to solve these slightly more applied problems as a means to an end. And so I think the class of problems I was interested in were like games under uncertainty, auctions and mechanisms, and really designing markets, trying to figure out how you can design institutions or rules of games to make them work better and work more efficiently.
But it seems that I guess the real world about the uncertainty is the critical factor to reason about in some ways.
In the theory of auctions, the idea is that the mechanism designer, the auctioneer, doesn't have all the information about how valuable an object is to the participants. And so part of the role of the auction is to get that information elicited and then use it to make efficient decisions. But the nature of the game can lead to efficiency or inefficiency. And how the bidders respond to that uncertainty, as well as how the auction design elicits behavior, can make a difference. So just one application of that, we looked at, for example, the difference between, for timber auctions, the difference between having an open ascending auction where people raise their hands until the auction ends, everybody drops out, versus a first price sealed bid auction where you send in sealed bids and then the winner is the highest bidder and they pay their bid. And so under some conditions, there's a beautiful theorem that says that those are actually equivalent. But then under real world conditions, there's a bunch of reasons they're not equivalent. And in particular, the ones where you have sealed bids are inefficient. That is, a weaker bidder can win. And it's basically because people shade their bids, and weaker bidders are more aggressive bidders, and they can sort of outbid someone who thinks they're likely to win and doesn't think they need to be so aggressive. So that seems like that's bad, and so you shouldn't do that. But it has this extra benefit in that it induces more participation of weak bidders. And so the bidders, sort of understanding that they have a chance to sneak in and win inefficiently, are more likely to participate. And that in turn can fight collusion and lead to more competitive auctions. And so I did a lot of research about that theoretically, and also working with data from real timber auctions to illustrate the magnitudes of those effects. And that those types of themes, that the rules of the game have these sort of direct consequences, but also these broader implications for how competitive a market is and who even participates in the market, is a theme that then I brought later to, say, the advertising auctions at the search engine at Microsoft.
Must be really exciting to identify one or more pathologies in a current understanding and or current implemented mechanism that lead to things like collusion, having big effects, and coming up with a new, clean, beautiful theory that addresses some open world issues that then give you a new, more bulletproof mechanism. Must feel good to have that take effect.
Yeah, and I think one thing that I think economics really trains you well for is trying to get a model with just the right amount of abstraction that it sort of can capture the important forces in the world. And then, but the model is also specific enough that it makes sharp predictions, and it can be hopefully taken to data. And some economic models really flunk that. They're too complicated, they're too unrealistic, and they just don't fit the data. But in mechanism design and auctions, it's been a real success of being able to build a theory that's actually useful and then calibrate it with data and make predictions. So one of the things that we did in the work on the two different types of auctions is we estimated a model or trained a model using just the data from the sealed bid auctions, the first price sealed bid auctions. And so we calibrated those models and we figured out on average what bidder preferences were. And then we predicted not just how they would bid, but also how many would even participate in the open ascending auctions without using any data. So it's a completely different game. And actually theory would suggest that actually half as many small bidders should show up at the open ascending auctions. So it's a really different game. But using just the data from the sealed bid auctions, we could actually do the counterfactual prediction of what would happen in this very different auction format and predict very successfully there. And so that's, most models, economics, would not be able to pass a test like
Right.
that. And it was really exciting to be able to do those kinds of counterfactual predictions.
So the this idea of we have models, they model some set of assumptions about the world. We run them in the world. We may or may not see challenges they have or problems they have from our evidence stream that we have in place. We might later find a bug or a problem, even when that's been long-standing, yet exogenous to our models and our understanding of the system, and then we have to go back and sort of cycle and somehow repair or come up with new theories to fix that. I'm curious how often that happens in economics these days. Is it less and less as we deploy these systems in more or less broad ways and observe and then refine them, or is it we still finding once in a while a major gaffe and oh my gosh, that doesn't work very well?
Well, I would say that models of the macroeconomy generally don't work very well. And so
Okay, so we're in good shape for research.
they have a
there.
long way to go. And it's not the people's
Yeah.
fault. It's just that at some level to like learn something from data, it's most useful if you have kind of experimental stimulus, or you can tweak one part and hold the other conditions fixed. And in the macroeconomy, it's just very hard to do so. But in microeconomic settings, like in this timber auction setting, they literally did an experiment and randomized which
That's
auctions
great.
were first price sealed bid and which ones were open ascending. So you really had that experimental variation, and you could use that to test the models. And we did try different models to make sure that we had ones that did the best job both in sample but also in counterfactual predictions.
And then there's always the interesting issue of, can we take this whole experience and new model to another domain and see if it still has the same effects?
Well, so you would build a different model. So the auction models are very specific. Everything about it is specific to that particular game. And so certainly that literature, we've been doing empirical models of auctions since the 1980s. And so they've gotten better and better and better. Broadly, I think the paradigm has stayed the same, but we've gotten, more flexible estimation techniques, and we've incorporated more and more richness in them. But you're also limited by the variation that's in the data. So another thing that economics puts a lot of emphasis on is causal inference. So we want to do, usually the main use case of an empirical economic model is to do some kind of counterfactual. You want to understand in microeconomics, what was the effect of the intervention? What was the effect of raising the minimum wage? What would happen if I changed my price?
The what would happen if kind of notions of the
Yeah.
counterfactual.
What ifs, exactly. And so for many, many years, we've had to actually do heroic things. So we've had to figure out, what would happen if two firms merge. And so a typical expert witness thing for an empirical economist would be to estimate demand for products and then say, well, if two firms merged and they maximized profits, how much would they raise prices? So these are all about worlds that we've literally never seen before. And those models, of course, are controversial because if they've never seen before, when I used to explain these to computer scientists, like, how can you build models when you can't validate them? This is crazy. Are you guys really even scientists if you do that? Part of the answer is, well, the Department of Justice has to make a decision, and I'm sorry, but I can't have the firms merge and then unmerge them. So I really do need to make decisions. But I would say that one of the themes of my research, which has really been reinforced by starting to interact with computer scientists, we should find ways to validate our models. And yes, we can't make the firms merge, but there may be things in the data.
You can generalize somehow.
Yeah, we can look at some things are not exactly like that are sort of held out data that's a little bit different than the data you use to estimate, and see how well you do for those held out situations.
Speaking of this, we've seen the rise of data-centric methods, the advances in machine learning, the ability to predict with confidence scores of various kinds. Can you comment a little bit about the rise and uses of machine learning in economics and economic modeling?
So this is still fairly niche in economics, but I feel like it's on the verge of exploding. And really, if I had to thank Microsoft for many things I thank Microsoft for, but one of them is that this is where I learned about machine learning, and I was introduced to machine learning by Microsoft researchers who were working in the Bing search engine. And so I think I was one of the first, if not the first economist, leading economist to say, hey, this is really big. And I think that there's things about machine learning that you can bring into economics that would really make things different. I should mention that in our first interactions, it was kind of this strange thing where I was an economist and I said, economics has been using data to make decisions and do analysis for decades. And really, we have never imported anything from computer science into doing this. We're expert witnesses. We run government agencies. We work on drugs and school class size and minimum wages. And computer science isn't even part of this conversation. How come you think that you actually have a way to do this better? And then the computer scientists were like, well, we're running a whole search engine. There's no economists here. We've never learned anything about econometrics. How could this possibly have anything to teach us? And actually what's been really exciting is that in the last 10 years, both sides, I think, have really realized that there's some interesting things to learn.
What are some of the, in your mind, some of the key touch points or synthesis opportunities that are coming to the fore with between computer science, particularly machine learning, artificial intelligence more broadly, and economics? Yeah,
so I think economics has always been good at they're really laser focused on counterfactual prediction, cause and effect, what if questions, but always in a small data framework. So you assume roughly you have 3 covariates and 1 million observations. And so we worked on flexible models, but in a very small data, a very small number of covariates setting. And we pretended that God gave us our model. The God of economics gave us the functional form. And actually, data mining was a pejorative term. That was what people did that were cheating. It was a synonym for p-value hacking. P-value hacking meaning keep testing things over and over again until you find something that fits your hypothesis. And so what I feel like we've really imported very well from machine learning into economics is this data-driven search for models and much richer classes of models and much better, more systematic ways to fit the data well. Where I feel that machine learning there's always been people in machine learning who've thought about causal inference, people like Judea Pearl, but it was really fairly niche, and you would meet machine learning people who really weren't very conversant in the framework and you could finish a PhD in computer science and you'd learn mostly about prediction, and so you would come.
Well, even that even describes Judea Pearl's life until 1988 or so, as I recall.
Yeah, but still today, a lot of people come out come out of a PhD, and in some sense, they've learned about prediction, about fitting data, and then you sort of, if you have this hammer, you feel like everything's a nail. But say if you take something like trying to do click prediction in the search engine. In fact, we're doing some counterfactual predictions because we're asking the question, what would happen if I took something from the third position and put it into the first position? And so you're actually doing a what if that sort of changes the environment away from the one that you used to fit the data. I think a lot of the tech firms will talk about things as if they are doing counterfactuals, but the algorithms themselves didn't account for that, and they were just fitting.
Yeah,
and
it's interesting. It's interesting. Sorry to jump, but it's interesting. You got me excited here by thinking about some of my conversations with Judea Pearl directly. It's been interesting how passionate he is about the core capability in any intelligent system, whether it be a human or the ones we're trying to build, to do counterfactual reasoning, to imagine, to envision possibilities that don't exist today or that don't exist here and now, and to imagine manipulations, actions, sequences of action that would change the world. And the fact that all of civilization came out of that capability, the pop of civilization came from this special human ability to do that well. Yet, largely we see today in AI prediction technologies, as well as applied in business prediction technologies, and that's been referred to as the AI revolution in many places. You sort of comment about that?
Yes. So I think that was really why I got excited about working on AI, why I thought I had something to bring to the table, because all of my training was about counterfactuals, but it was applied to very simple data sets and really simple problems. With these huge new data sets, as well as opportunities in tech firms to intervene and run lots of experiments and things like that, there was a possibility to learn about cause and effect at a much grander scale. And so I want the theoretical insights from people like Judea Pearl or Don Rubin that set up a framework for thinking about this. Those theoretical insights can be implemented in a much richer way when you combine the computational techniques and the estimation techniques from machine learning to do things like personalization and to control for lots of covariates, but still maintaining the rigorous theoretical focus on cause and effect. So just as an example, in sort of old-style economics, we might have said, let's look at the average effect of changing a price. And then we might run an experiment with price changes, or it might be that there's some natural experiment in the past, something that caused the price to change that was unrelated to consumer demand. But we would estimate an average effect. Machine learning has gotten really good at personalized predictions. So you can adapt a lot of the algorithms from personalized prediction or just personalized fitting, like saying, okay, which of these people is going to click, or which of these people is going to buy. And then you adapt those techniques to answer the question, for which of these people will a price change cause them not to buy or cause them to buy? And so it's not a huge leap computationally and algorithmically from one to the other, but there are also some key insights that are important to recognize when you get there. So let me one way we talk about this in economics is we call it identification. We want to know, if I had an infinite data set, could I possibly answer my question? And for causal questions, if you have a randomized experiment that varied the treatment, then it's pretty clear that I can learn about cause and effect. But what if I don't? And there's a lot of question of work in economics about what you could do if you didn't have an actual randomized experiment, but there's still something in the data that varied that could be used to find a causal effect anyway. But it's very delicate getting that done.
And how do we deal with, these days in economics, with causation under uncertainty, where you have a probability distribution over a causal effect or the impact of a cause?
There's different branches of dealing with that. So in the classical approaches, we would estimate a model, and there would be a confidence interval around the effect. So I would estimate a price elasticity. Price elasticity means how responsive is say a market to a price change, and then I would try to get an unbiased estimate of that price elasticity and put a confidence interval around it. A lot of the machine learning models actually don't have good statistical properties, and you wouldn't necessarily be able to get an estimate of a parameter out of those models that's centered on the truth. So one of the focuses of my theoretical research has been to provide the statistical foundation for popular machine learning models. And I focused on random forests because they are amenable to statistical analysis, and they work pretty well for a class of problems.
And as others might say, you can always do bootstrap to get some statistics and some properties over even models that don't have the foundational properties you want.
Yeah, exactly. So, I mean, and of course, neural nets have eluded a lot of theoretical analysis, but actually, for some problems that are a little bit simpler, like economic data sets where you might have monotonicity or curvature, we have modified versions of random forests that do things like bias correction or combine linear models with the random forest that will do a pretty good job fitting data that's not quite as complex as like images. And then we've provided the statistical guarantees so that people can then get what they want, a parameter estimate and a confidence interval. We also have a tradition of Bayesian modeling in economics, which has always been more niche, but that tradition...
That's unfortunate.
That tradition actually meets very well with the computer science tradition. And actually the work I'm going to present today is in the Bayesian tradition. I'm working with David Bly, who's a computer scientist at Columbia.
Good friend.
Yeah, and he's gotten very interested in these causal models. So we've been, and Bayesian models are actually very amenable to more complex counterfactuals because you're generally writing down a data generating process. And so that data generating process, in some sense, is a model of how the world works.
Exactly.
And so I guess coming back to your question about AI, let me elaborate on that a little bit more. Economics has sort of two categories of counterfactuals that we might do. One is like there's a treatment a minimum wage or even a price increase. And some people in the data have experienced that change, and we're just trying to figure out what would happen if everybody experienced the change, or what was the comparison between people who had the change and people who didn't. But it's always something that's actually happened in the world, and that's really the program evaluation or treatment effect literature. There's another literature which tries to be more ambitious, but also requires more assumptions. And this is the literature that would say, what would happen if two firms merged? What would happen if I raised a price that has never been charged before? So of course, you have to have some extrapolation. If for things like raising prices, though, maybe the extrapolation isn't too crazy. If you could really learn about consumer preferences from seeing the choices they make, and you extrapolate carefully, you can have a pretty grounded view of what would happen if a price went someplace you've never seen before. So models, though, you need more functional form assumptions for that, because if you're just fitting in a data set you have, things can go wildly wrong without any functional. If you don't have any functional form assumptions, things can go wildly wrong if you go outside of the range of the data. While these sort of more structured models that build up and say, I'm gonna estimate for each consumer based on their past behavior how they feel about prices, then I can extrapolate to a situation where I present the consumer with another choice. And similarly, we can model firm profit functions. And if we can understand the parameters of a firm profit function and we assume they maximize profits, then I can evaluate what they would do in a situation they haven't been in before. Or a bidder in an auction, if I understand their preferences, I can understand how they would play a different game.
Speaking of preferences, in the mid-90s, I and colleagues worked on recommender engines, even Bayesian versions of these. And the idea was we would assume static preferences of the users coming into a service, for example, and we would pose for assessment examples, movies, for example, like this movie, yes, no, to come up with a probability distribution over their preferences and, of course, items that they would prefer or choose. And we would use value of information computations. We'd say, okay, what's the next most valuable item to assess to maximally get to the core of static preferences without worrying about causality at all in those days. And I'm guessing, and I know for certain companies, this is still the way recommender systems work. You might like to buy this book versus doing richer causal reasoning. Can you critique the older way and the assumptions versus what you do today if you had unlimited time to assist and unlimited compute and data?
Well, so I think that the connections between what you were talking about there and what we're doing today and promoting today are tight. And I think in some sense, like Bayesians are Bayesians, whether they're economists or computer scientists to some level, because you are writing down a generative model of the world.
Right.
And that is basically what economists do. They write down generative models of the world, which impose assumptions.
Right.
And I think if you're going to extrapolate, you need assumptions. And I think that's really a core point for AI. If you want an AI to work in the environment you have, that's awesome. If you want the AI to do anything outside of the environment it's experienced, then suddenly you really need models, because you need to know how to extrapolate from what you've learned. And so I would say that I think that recommender literature is actually great. You're writing down a generative model. You're trying to learn the parameters of the model. The things that we might add in would be thinking harder about what variation in the data really allows you to learn things. So if you just had historical logged data and you were only using that historical logged data, it could be that the things that people were shown in the past were not accidental. And somebody was shown something and they chose it because of characteristics of that person.
A causal effect in the sampling, basically, an unmodeled set of assumptions in a sampling procedure.
Yeah, exactly. And so then one of the things economists or causal inference people in statistics might add into that is to say, okay, you either needed to actually only work from experimental data where the choices that people saw were randomized in some way to really understand their preferences, or if the logged data was generated from a process, then you need to estimate aspects of the process that generated the data to control for the selection effects, to control for the fact that some people picked book A, but that was because they were never shown book D, and other people picked book D, but they were never shown book A. And so you need to correct for the fact that not everybody was shown the same thing and in making their choices. But to some extent, I think in some applications, you might have been working with logged data that was fairly clean, and those problems wouldn't make that big a difference. While in other settings, like when I looked at this in Bing Ads, these problems were really big. And Leon Batu was a scientist at Microsoft Research for a while, and he was very interested in these ideas as well. And we worked together on some things, and he did a bunch of additional work on showing the difference between experimental estimates. He basically got us to run experiments, and so you could compare what you got from purely experimental data and from the log data using the machine learning methods in practice, and you could show and demonstrate that you got the wrong answers from not taking additional steps to compensate for the fact that your data is not experimental. And so I think we have great techniques for doing that kind of compensation in small data settings, but I think we still don't have them at the right scale to be. I think there's still room for improvement in big recommendation systems today, because we haven't figured out how to fully and optimally scale those techniques to production size problems.
Let me change, just to pivot a bit onto careers. You seem to be very excited about the things you're doing. You love these ideas, and you've made a set of career decisions over time to bring you to this place. And of course, for every person, we're all different, and we can do what ifs, of course, for their own lives, and imagine where we might be. But you've gotten to a really fabulous place, I think, from the outside looking in. I'm curious if you have some career advice for others right now as they do their what ifs out there in the viewers watching this that are thinking about careers, even in economics or computer science or related fields.
Sure. So I would say the first 12 years of my career were very successful, but I was working in a very mature field. So I told that some of the timber auction work I talked about, it was beautifully executed. It laid some good role models for other people to think about validating these structural models and so on. But ultimately, I would say none of it was actually path-breaking, because all the fields that I was working in had the paradigms were established when I was born as an economist. And I was always jealous during that time period of the people in the 1980s had laid the groundwork. The real conceptual insights came in the 80s before I was born as an economist. And we could extend them and expand them and improve them, but didn't really feel fundamental. And so actually when I got the call to come work for Microsoft, I got a call that said, "Do you want to come meet with Steve Ballmer?" I said, "Sure." And then he was like, "Yeah, I think we kind of need an economist to think about this online stuff." And I was like, "Okay, sure."
This online stuff. Yeah.
Yeah, they're like, "We're pretty good at Windows. I know how to do that. I don't think we really understand how to compete with Google." And that was sort of a crazy thing for me to do. I was a professor at Harvard. I had just gotten this big prize. Everybody loved what I had done to date. I should have just kept going in what I was doing.
You say big prize, by the way. This is like the Nobel Prize in economics for a young economist.
Yeah, so I was, and that's actually how Steve found out about me, because there was a big article about me in the paper. And so the natural thing to do would have been to just be great at what I was great at. And I had I was working on, we at that point defined the field as market design, which was bringing theory and data together to solve like auction problems and school choice problems and things like that. And I was well recognized as sort of the young, not the old leader, but at least the leader of my generation, a leader of my generation in that. But then the opportunity came to come to Microsoft, and I was seduced by this idea of, I went in and I looked at the search engine, and it was just wide open. And I realized right away that my economic tools were not up to the task, actually. Like, this was harder and broader and more complicated. But at the same time, I had the instinct that there really was economics here and there was value to add. So I felt like from the business perspective, there were all these amazingly brilliant engineers, but they didn't know about advertisers or prices or auctions or things like that. But also I learned that they weren't as familiar with causality, and that was also very important for thinking about what would happen if we changed our auction, what would happen if the prices changed, what would happen if we introduced this new product. So there was a lot of contribution from the data side as well. And so I think from the advice perspective, I would say that I think what I correctly saw was that here was something that was wide open. It was greenfield. The conceptual film. I mean, yes, I was building on the shoulders of giants at some level, but I could actually help lay some foundations. But I also, in some sense, had to take a big risk because for a while, first of all, I was just very busy trying to do this business work with Microsoft and build stuff and learn stuff. And, I didn't know SQL and I had coded in C, but not in all these other languages that were being used in production.
But you had great experience as an administration person for a Unix system.
Yeah, I had a CS degree. But, when I did it, we learned Prolog and Lisp and all these other stuff, so it wasn't very relevant CS degree. But so I had to, and I didn't know anything about machine learning, and I didn't know any of the jargon there. So I had to learn, and so there was a bit of a lull in my CV because I was, working building stuff, and because I had to learn all these new disciplines. But I think that was, and then also a lot of the economists were telling me I was crazy. Oh, this big data stuff, that's just description. That's not economics. Machine learning, that's just fitting. Like, that's not for us. And so there was a lot of pretty aggressive negative feedback from my colleagues as well. But I saw this, and I was just so sure that there was something there. And I was also sure that it makes a big difference to be a leader. If you get there first and you're smart, and you're humble and learn, you can be a leader. It was very likely I could be a leader here in a way that I hadn't been before. There's a difference between getting tenure and getting prizes and actually really being a leader and defining a field. And so this was my chance to kind of do that. And I took the chance, and it paid off, and I'm excited about that. But it did require being humble, like going out to a computer science conference and be like, who the hell are you? And there was a lot of stuff I didn't know, and there's a lot of stuff I still don't know. So it required taking a lot of risks. But I broadly think that there's sort of then these two takeaways. One is find something that's young, where you can make a difference. And then the second thing, though, is to be a little bit differentiated. Because in some sense, if I was just one in a sea of, if I just completely tried to be a machine learning person, why would I be the best one? But I found a niche where I knew I had something to bring to the table, special expertise. And then there's more of an ability to make a contribution. And so maybe for the young people today, there's a little bit of sense of that, there's some things that are getting maybe a little overdone in AI. And so you want to be a little bit ahead of the game rather than behind the game. And I would say at some level, like this pure prediction problem is just going to be commoditized to some extent. Like we're going to get self-tuning neural nets, and the AIs will tune the neural nets.
You're giving away all of our secrets now.
And we'll that part will be more commoditized. But then there's still a conceptual part of really understanding how it works and why it works, which was foundational to figuring out what the next breakthrough is. And so I guess I would suggest that the tide is going to turn back to a little bit more conceptual insight. And this, if we really want to get to human-like learning, there actually is a sense in which just fitting is going to hit a wall. And so we're going to have to bring back combine that with some modeling, because it's just a fact that you can't extrapolate without a model.
What do you think some big feasible surprises in the field of economics will be over the next 15 years? Like, what kind of things might happen, even if I could describe them a little bit more abstractly, that would be almost surprising from today's point of view, that will rely heavily on economic inferences and models and their use in the world? Well,
I think at some level, there's different parts of economics. So I think in some level, the economic ideas may not change. If I see something where the data is going to come in, it's going to be that personalization kind of changes our insights. So there's a whole bunch of some like findings right now that stuff doesn't work. Like we go out and evaluate training programs, and like they do a little bit, but they don't work that much. But the typical of economic measurement of a government project or something like that is that it doesn't work. But a lot of these things...
The actual model doesn't work, or the government program
the program doesn't work. And so there's a lot of
or both.
There's a lot of negativity.
Yeah.
Like, things, educational interventions don't work, health interventions don't work. But I think that what we've learned from tech companies is that you shouldn't think about coming up with one grand idea and then go out and spend a year testing that one idea, but rather you iteratively improve.
Run flights.
Run flights, but lots of them, and you incrementally improve. So I believe that the economist is going to become much more of an engineer, because some of these economic problems, like retraining the workforce, finding government programs that work, are going to be recast as digital programs. Digital programs are amenable to incremental innovation. And so we will kind of join up with the engineers and come up with methods to incrementally improve. And so where that meets the current machine learning literature is in kind of bandits, contextual bandits, reinforcement learning, and that side of AI, which has always actually had a bit of a causal bent to it, because you're trying to understand what works, what treatment to give. And so that's going to come together. So my prediction is that economists are going to become more engineers. And instead of complaining that nothing works, we're going to start building things that do work to achieve economic outcomes, to make governments more efficient. But economists are interested in resource allocation, so we're going to do that on resource allocation problems, pricing problems. And so we're going to both figure out what works, but we're going to realize that nothing works if it's one size fits all, but that a lot of things work if they're actually personalized and appropriately delivered with the correct information.
Can you even imagine someday seeing a congressional hearing about how much to explore versus exploit in a program? It'd be fabulous.
Well, I think that's actually not so crazy. I mean, when I teach to business leaders and boards of directors and stuff about AI, and actually what they need to do at some level, the high-level leaders of a firm, is figure out how to regulate the AI. They need to figure out what guidelines should I be setting, what makes it safe, how do I make sure it's good. And governments have the same role. The banking regulators have to figure out how do the AI that are used in banks, what makes it safe, what makes it fair. So this broader view of sort of regulating and setting the objectives for AI is going to be hugely impactful. And so that's partly why you might have asked in my previous answer, why would economists have anything to do with this? But actually, when the AI is solving an economic problem and it's living in a real-world setting, what it optimizes, what are the measures? How do you judge success? What constraints do you put on it? Is it a decision support tool, or does it actually make the decision? All of those...
And whose values?
Whose values are represented. All of this stuff, but it really becomes, you can't decompose the problems. It becomes an integrated problem, and that's why I feel like these interdisciplinary teams will work together to create these, but I feel like we're actually going to do a lot of good in the world.
On that note, thanks very much, Susan.
Thank you.